Okay, so we are gonna do the warm-up, and you're definitely gonna want to have your nomenclature periodic table as a reference, and every single person needs to have one because doing this section really requires it. So a while ago, we did nomenclature. It was in chapter 2, and so if you're gonna calculate the charge on this metal right here, how would I go about doing that? Where do I start? On the right. So I've got 3 chlorines. What's the charge on chlorine? -1. When you multiply these two, what do you get? -3. So that means you would need a +3 on the other side. If I have 1 iron, 1 times what charge would be +3? 3. Okay, so that means the metal charge is +3. And then when you go to name it, you have to include a Roman numeral because iron doesn't have an assigned charge. We have to indicate what the charge is on the metal. And then we would end the chlorine and ide. So this Roman numeral 3 came from this +3 charge that we just figured out, okay? If we're going to do the same thing for the iron in the next section, you have acetate in parentheses, and I have 2 of them. What's the charge on acetate? -1. So these multiplied are a -2. I get a +2 on the other side. If I have 1 iron, 1 times what charge on iron is +2? 2. Okay, so the metal charge is a +2. And when you name this, this would be iron. Roman numeral 2 because of this charge that we just determined. And then you always name what's inside parentheses. So this would be acetate. Okay. And then for the next one, if we're going to calculate the charge on Mn, what's the charge on BrO3? -1. So 2 times -1 is -2. That means I need a +2 on the other side. If I have 1 manganese, what's the charge on manganese? 2. So this would be a +2 metal ion charge. And then the name would be manganese. Roman numeral 2 because of this charge on the metal. And then since we have parentheses, you name what's inside the parentheses. BrO3 is bromate. Okay, for the next one, what's the charge on oxygen on the periodic table? -2. So -2 times 2 is -4. Agreed? And if I have 1 manganese, the charge on manganese would have to be what? 4, right? Because these multiplied would be a +4. So when you go to name this, this would be manganese, Roman numeral 4, oxide. And then the last one, do I need to calculate the charge on K, or does K have an assigned charge? It's assigned. So this is potassium. And then what is the name of MnO4? It's on the bottom left of your periodic table. Yeah, permanganate. Okay, we good? Okay. Today we're going to talk about oxidation reduction reactions, which involve the transfer of electrons. Can I move this screen down? Okay. So when we're dealing with electrical chemistry, which is converting chemical into electrical energy or electrical energy into chemical energy, we're going to be taking a look at reactions that involve electron transfer, and we commonly call these oxidation reduction reactions, but since it's such a long name, we can abbreviate it as redox for short, okay? There are certain kinds of chemical reactions that transfer electrons between them. One of them is a synthesis reaction, another one is a decomposition reaction. And the types of synthesis and decomposition reactions that you would need to have are the kinds that have a elemental form of something. So if one of the reactants is an elemental form, awesome, then a redox reaction will occur. We also have single replacement reactions and combustion reactions that fall into these categories. So I have 1, 2, 3, 4 different categories of reactions that involve a transfer of electrons, okay? So when I say elemental form, that means if you have something like magnesium combines with chlorine to make magnesium chloride, this is a synthesis reaction, and then magnesium and chlorine would be considered an elemental form. That means it's that pure element. It's fine if it has a subscript on it, like if it's diatomic, or if it's like phosphorus, like P4 is a common way to represent phosphorus, or S8 is a common way to represent sulfur. Also, if it's a decomposition reaction, like if you have water decomposing into hydrogen and oxygen, these would also be elemental forms of hydrogen and oxygen. So this would be considered a redox reaction as well, okay? If you have another type of reaction like double replacement reactions tend to not involve electron transfer. So chemical reactions that do not involve electron transfer are called metathesis reactions, and that's the last definition that's at the bottom of the page, okay? So let's turn to the next page and let me outline how we follow along and determine oxidation numbers, okay? Okay, so on the next page, they talk about oxidation numbers, which are often called oxidation states. They're the same thing. They're sort of like these imaginary numbers that we use to keep track of the electrons that are transferred between a chemical reaction, if they are at all, okay? So the rules for determining oxidation numbers or oxidation states are given in a table on this page. A lot of the oxidation numbers are the same as the charges that you have on your periodic table, so that's why you have that out as a reference. So I'm going to go over these 8 rules, and then we're going to do some practice problems on the next page. Why won't it stop? There we go. Okay. All right. First one. Atoms in elemental form have an oxidation number of 0. They have given us a number of examples off to the right-hand side. They've given us elemental sodium, oxygen, phosphorus, arsenic, and zinc. That means all of these have oxidation numbers of 0. We tend to write those numbers above the symbol. Okay? Now, the second rule is if you have a monoatomic ion, that means the oxidation number is the same as its charge. So here, I've got K plus 1. So I'm going to write a plus 1 above it because that's the same as its oxidation number. Ca plus 2 is a plus 2. Fe plus 2 is plus 2. Fe plus 3. And then Cl negative 1. So you'll notice all of the charges on the monoatomic ions are the same as their oxidation number. Okay? Third rule. Oxygen is usually a negative 2. Okay, so that's the same as its charge on the table. That's easy to remember. There are 2 exceptions. The one is if you have peroxide, it's a negative 1, and the other one is if you have OF2, then it's a positive 2. So how do I know if I have peroxide? Okay, so the trick for peroxide is it should be a metal with peroxide. So if you have a metal with an O2, be a little suspicious that it's peroxide. Let me give you an example, okay? Over here, they give me Na2O2. So Na is a metal. It's a metal attached to O2, so you should be suspicious that this might be peroxide. So the way that I would do it is make yourself a note that the alkali metals have an oxidation number of +1. The alkaline earth metals have an oxidation number of +2, and any other metals on the periodic table with assigned charges, like aluminum, which is +3, or zinc, which is +2, or silver, which is +1, these are all of the oxidation numbers of the metals that have assigned charges, okay? So use that to reveal if peroxide is present. Sodium is an alkali metal, okay? So if sodium is an alkali metal, we would put a +1 above it as its oxidation number, okay? Oxidation numbers add up to 0 if you have a neutral compound, which I do here, okay? So if sodium is a +1, oxygen has to be a -1 to allow them to add up to 0. Does that make sense? Okay, so what I just did is I did Rule 5, where it says oxidation numbers in compounds must sum to 0, okay? And then if I apply the same rule to OF2, where it says that O is a +2. So if you put a +2 here on O, wouldn't F have to be a -1 in order for those oxidation numbers to add up to 0? Does that make sense? Okay. Now, make another note that generally speaking, the halogens are going to be a -1, which is the same as their charge on the periodic table. It also has something to do with the fact that they're usually the most electronegative element, or commonly a highly electronegative element in a compound, which I'll get to in a second. Okay, let's go on to rule number 4. Hydrogen. Hydrogen tends to be a +1, which is the same as its charge on the periodic table. The exception is if you have a metal attached to hydrogen, then hydrogen is a -1. So let's take a look at that. Over here, calcium and lithium are metals. Okay? Calcium is an alkaline earth metal. So what would its oxidation number be? +2. Okay, so that makes hydrogen a -1 because that's the only way for those oxidation numbers to add up to zero. Does that make sense? So this is your metal hydride example with H as a -1. Here, lithium is an alkali metal. Alkali metals are +1. That means hydrogen is a -1 because they add up to 0. Yes? Okay, let's go down to rule number 6. Oxidation numbers in polyatomic ions add up to the charge on the ion. So let's do these 2 examples, and I'm going to write these out for you. They gave us ClO4 -1 and ClO3 -1. You always start by assigning what you know. You know that O is a -2. So we're going to write a -2 here above the O's. Do I have you so far? Okay. Then we're going to calculate the chlorine in each one. Okay. The way that we do this is by basic algebra. So if I have chlorine plus I have 4 oxygens at a -2 here, these add up to the charge on the polyatomic ion, which is a -1. What is 4 times -2? -8. When I put the -8 on the other side, I get chlorine is a +7. Okay. If I'm doing that on chlorate, I have a chlorine plus 3 oxygens at a -2. And this adds up to the charge on the polyatomic ion, which is a -1. So Cl minus 6 is a -1. Chlorine is +5. Okay. Did I lose you? We're good? Okay. 2 more rules and we're done. Number 7. If you have a compound, always assign the more electronegative element a negative oxidation number first. Usually this is if you're dealing with a molecular compound. You know that electronegativity increases up and to the right on the periodic table. And fluorine is the most electronegative element. So if you assign fluorine a -1 because it's the most electronegative element, then wouldn't that make P a +5? Because the oxidation numbers add up to 0. Last rule. If you've got a really complicated compound or an ion that's got more than 2 elements in it, assign the element furthest to the right, which would be nitrogen in this case. Assign it its usual charge. What's the usual charge of nitrogen? -3. Then look at S and C. Which element is more electronegative, S or C? S or C is more electronegative, S. Okay, what's the usual charge on S? -2. Then we'll calculate C. -2 plus carbon plus a -3 on nitrogen equals this -1. So it's C minus 5 equals -1, carbon equals +4. Hold on.